Hello everyone. So let us have a look at this particular problem. Now in this problem there is a massless rod, almost inertia-less horizontal rod whose length is 2 times small l. That means it is small l on one side. And on this rod are put two beads which are attached by a string whose total length is 1.2 times l. That means the length on one side is 0.6 l. And initially the entire system is spinning about this particular axis at an angular speed omega. Omega's value is also being given. It is 1 by 3 radian per second. Now when the rod is spinning about this particular axis, this bead B requires a centripetal force which is provided to it by the tension in the string. A needs a centripetal force which is also provided to it by the tension in the string. It's T on both the sides, so the system is initially perfectly fine and easy to understand. Now at some moment the cord is cut. Now once the cord is cut, B will start sliding outwards on the rod and A will also start sliding outwards on the rod, and they are asking us to find out which of these options are correct, A, B, C, D. Two of them they refer to the kind of path that the bead is going to take, and two of them they refer to the amount of time that the bead is going to take to go from its initial location towards the end of the rod. So let's say that the rod initially is this and there is an axis going through its center. It is spinning about this particular axis. There is a bead B which is initially at a distance of 0.6 times L from the center of the rod. Let me call that distance as small a in order to have a shorthand notation. The length of rod on one side is capital L, and so the total length of rod is 2 times of capital L. Now this is the initial situation in which the rod is, and after the string is cut, B starts sliding out. So at any given moment later, the system is going to look like what I am drawing here. This object B is at a distance of small l away from the center now, and its motion is analyzed by an observer who is standing on the rod at exactly the same place. So this observer is also spinning along with the rod. He has an acceleration towards the center, so he will apply a pseudo force on this bead B away from the center in the outward direction. Right now the pseudo force that he applies on this bead in the outward direction will be m omega square r, where omega is the angular velocity of the rod at that particular instant. Now I'm saying that particular instant because they have not said that the angular velocity of the rod is maintained at 1 by 3 radian per second. That was the initial value anyways. But as the beads they start moving outwards, the moment of inertia of the system about the central axis changes, and so the angular velocity should also change in such a way that the total angular momentum of the rod remains conserved, because there are no external torques acting on this particular system. So if that is the case, then I can say initially for this mass B, the angular momentum about the central axis will be m v times r, and there are two of these beads, so into 2. So this is 2m a squared omega, and finally both the beads will be at the same distance away from the center because of symmetry. So small l here and small l there also for the A bead. That means the total angular momentum of the system is 2m l squared omega prime, such that 2m a square omega is equal to 2m l squared omega prime. That will help us to figure out what is omega prime. Therefore omega prime is equal to a squared omega by l squared, number 1. Now this person, this observer, will draw the FBD of bead B, and he will draw a force on bead B in the radially outward direction. The force will be omega prime squared times L, m omega square r. That's the force, where I'm using the omega at that instant and the length L, or the value of the radius at that instant. So the acceleration of this bead will be omega prime squared L, which is, because I know omega prime square is a squared omega by L squared whole squared times L. and because the acceleration is in terms of a distance, I will try to write this as v dv by dl instead of saying that it is dv by dt, right? So v dv by dl. So the final equation that you are going to get for the acceleration of this bead looks like v dv by dl is equal to a power 4 omega squared by L cube. There is a L power 4 and there is a L in the numerator, so L cube, and then you will have to integrate this. You will get v squared by 2 is equal to a power 4 omega squared times L power minus 3 dl, an integral of that, and you will get v squared by 2 is equal to a power 4 omega square. This is L power minus 2 divided by minus 2, so minus 2L squared plus, of course, a constant of integration that we will have to determine. Now how do we find out this constant of integration? Initial conditions: when the value of small l was equal to a, that was how the bead B was initially. At that moment, the velocity of B along the rod was 0. It was spinning along with the rod, but along the length of the rod, it wasn't moving in any manner. So when small l is equal to A, so please have a look at the right hand side. If small l is equal to A, when small l is equal to A, V is equal to 0. This gives you 0 is equal to a squared omega squared by 2 plus c, negative a squared omega squared by 2 plus c. So therefore c is equal to a squared omega squared by 2. This will give us the expression for velocity of the rod as v squared by 2 is equal to a squared omega squared by 2 taken common, and within brackets you are going to have 1 minus a squared by L squared. So this will give you v is equal to a omega by L multiplied by root of L squared minus a squared. Let us keep that equation in our hands, call that equation 2 perhaps. Okay, now after we have this equation for v, we will need to figure out what is the value of L as a function of time. So you can write v as dl by dt, and you can try to solve this particular equation, which is in fact pretty easy. So dl by dt is a omega by L root of L squared minus a squared, and L dl divided by root of L squared minus a squared is equal to a omega t. Now this can be solved very easily using a basic substitution. You can take L squared minus a squared as some new variable, and when you do that, L squared minus a squared is equal to z, so L dl is equal to dz by 2. You will get in the original equation here z raised to the power minus half dz by 2 is equal to a omega t plus c1, and I should have added that c1 here also. I have not added it, so this is c1, a new variable of integration, and I will have to integrate the left hand side because here I have already integrated the right hand side. So there is an integral, there is an integral here, and this term can be found out. This is z raised to the power half divided by half, and that divided by half and this half is going to cancel out, so only z raised to the power half, and z itself is L squared minus a squared. So you are going to get root of L squared minus a squared is equal to a omega t plus c1. And how do we determine the value of c1? Again using initial conditions. So on the right hand side, we know that at time t is equal to 0, the value of L is small a because that was the starting point for the bead. So L is a, and so therefore c1 will become 0. So this is your final equation, root of L squared minus a squared is equal to a omega t. And he's asking us to figure out the time when the bead reaches the other end of the rod. Now when the bead has to reach the other end of the rod, small l should become capital L. The length on one side was capital L. When small l becomes equal to capital L and the value of a is anyways known, is equal to 0.6 times L times omega, which is 1 by 3 times time. And this will go with a 0.2, so this becomes 2, this becomes 8, there is a 4, L cancels out, so t is equal to 4 seconds. So we have been able to find out the time at which the bead will be going out of the rod or leaving the other end of the rod. This is t is equal to 4 seconds. So at least we know that option C is correct. C is one of the correct options. Now for the second part, the path of the bead. So what I'm going to do is I'm going to show you the top view. Now let us say in this particular view, x-axis is to the right and z-axis is to the top. That means the y-axis is in fact pointing into the screen, so this will be y. And if you have an observer looking at this entire thing from the top, this place, then this observer is going to look at the x-axis towards the right, and he will be able to see the y-axis going this way and the z-axis will be going towards the observer. So he will be looking at the z-axis like this. And let us say, according to this observer, the moment when the bead was cut was the moment when the rod was aligned along with the x-axis. And after that, the rod kept on turning around, of course, about the z-axis, and the bead kept slipping away from the center of the rod, and at one moment it moved out. So what will this observer draw? So what this observer draws is maybe a diagram of this kind, where the rod at t is equal to 0 is aligned with the x-axis, and at some other time t, the rod has turned by some angle theta, where theta is not easy to find out because the angular speed of the rod in this case is a variable, and the bead B, which was initially at a distance of a equal to 0.6 L from the center, is now at some other distance L from the center. Now at this moment we have the bead at some x comma y coordinate, and we want a relation between those x and y coordinates so that we can figure out what is the kind of path that the bead takes. Now what will be the x coordinate of B bead at this moment? At this moment we can easily say that x coordinate will be L cos theta and the y coordinate will be L sin theta. The issue is we have a variable L, we have a variable theta. So theta varies as the time changes, and it's not easy to find out theta because it is integral of omega dt. And L itself is a variable. It is a into root of 1 plus omega squared into t square that we have calculated here. So if you rearrange that equation, you will get that L will be a square, L square will be a square plus a square omega square t square, squaring both sides and taking a square to the other side. And so therefore L will simply be a times square root of 1 plus omega square t square. So L is a variable and theta is of course going to be a variable. So how are we going to solve this? How are we going to get the values of x and y? In this case, probably we know the value of d theta by dt at this instant. D theta by dt at this instant is the angular velocity of the rod, which is omega prime, which should be a square omega by L square. We have found that above. So therefore, and I'm doing it here, you can say that d theta by dt will be equal to a square omega by L square was a square into 1 plus omega square t square, from where a square will cancel out and you will get d theta as omega divided by 1 plus omega square t square dt. And here we can easily see that if we integrate the left hand side, we are going to get a theta. If we integrate the right hand side, we are going to get a tan inverse function, and of course we will have a constant also which can be determined. That's not a big problem. We can say that at t is equal to 0, theta is equal to 0, the rod was aligned with the x-axis, and that probably is going to give us that constant as 0, because in the tan inverse function, if I put t as 0, I will get a 0 and theta will be 0, so I don't have to worry about the constant. But how can I integrate this? I will get theta is equal to omega times integral of dt, and I will take omega square out, and I'm going to get 1 by omega square plus t square. And I know that the standard formula is integral dx by a square plus x square is 1 by a tan inverse of x by a. So we can use that formula here, where 1 by omega square plays the role of a square. So a will be just 1 by omega, and omega will flip up. So omega will go into the numerator here, and omega will also go into the numerator here, and the variable is not x, it is t. So you will get theta is equal to omega times another omega square is present here in the denominator, so that comes here. Then when you integrate that, dt divided by 1 by omega square plus t square, omega will go up, tan inverse of omega t, and you are going to get tan theta as omega t. So theta varies with time in such a manner that the value of tan theta will be equal to omega t. This omega is the initial omega, and t is that time. So if it was a constant angular velocity, then angle theta itself would have been equal to omega t. But in this case, the angular velocity is not constant, and so tan theta is equal to omega t, which we have obtained by solving this particular set of equations. D theta by dt is equal to all that much. Now this allows us to create a triangle with one angle as theta. Tan theta is omega t, so opposite is omega t, the base is 1. The hypotenuse will be root of 1 plus omega square t square. And from here I can figure out the value of sine theta and cos theta at any instant of time, and I can insert it in this equation to find out the x and y coordinates at any point of time. So what will be the x coordinate? The x coordinate will turn out to be L, that is a times root of 1 plus omega square t square times cos theta, which is 1 divided by root of 1 plus omega square t square, which will give you a. So x is equal to a. That is wonderful. And y will be L, which is a root of 1 plus omega square t square times sine of theta, which is omega t divided by root of 1 plus omega square t square, which is a omega t. So this helps us to understand that the x coordinate of the object is always a constant of this bead B. So the x coordinate of bead B is a constant, while the y coordinate increases linearly with time. So if you look at the motion of bead B, what's going to happen as the rod rotates is the rod will be like this at some moment of time, then the rod will incline slightly, then the rod will incline further, then the rod will incline a bit more, and so on. And the bead B, which was initially present at some location B0, will be found at a location B1 after some time, will be found at the location B2 after some time, and it will leave the rod when the rod reaches a configuration such that the free end of the rod is at this x coordinate. So they can also ask you the angle that the rod has turned by the time this bead goes out, and that can also be calculated. But from this we understand that the path of this bead must be a straight line. In such cases where the angular velocity is a constant, the path in fact turns out to be a spiral, but this is a different question. The angular velocity in this case was not a constant, so the path does not in fact turn out to be a spiral. It turns out to be a perfect straight line according to the situation here.